Hey everyone! Let's kick things off with a really interesting question. Why doesn't the heat from a hot cup of tea just keep going on and on? Or how about, why does a stretching rubber band feel warm? Both of these scenarios are connected to three concepts you'll be mastering today: heat, internal energy, and work. So here's the deal: heat is energy that moves from one system to another because of a temperature difference. Picture it like a game of tag, the heat tagging the cooler system and transferring energy. Now, internal energy is a bit different. It's the total energy stored inside a system, all thanks to the microscopic motion of atoms and molecules. So, when you boil water, the molecules are moving faster and gaining energy. That's an increase in internal energy. And lastly, work. That's energy transferred when a system undergoes a change, like when a gas expands and pushes a piston in a car engine. This is all tied together by the first law of thermodynamics, which says delta U is equal to Q, W. This equation basically says the change in internal energy, delta U, is equal to the heat added, Q, minus the work done by the system, W. Think of it as a balancing act between heat and work. Both play their part in changing a system's energy. Let's zoom in a bit more on heat and work. Heat moves in three ways: conduction, convection, and radiation. Conduction is like when you're holding a metal spoon in a hot cup of coffee. The heat moves from the hot liquid to the spoon and eventually to your hand. Then there's convection, which happens when hot air rises, like the warm air in your kitchen when you're baking a cake. And finally, radiation. That's how the sun heats the earth, with invisible waves of energy flying through space. Now, about work. If you've ever pushed against a wall and wished it would move, you've tried to do work. In thermodynamics, work is the energy transferred when something moves due to force. A simple equation for work is W is equal to P asterisk delta V. Now let's talk about internal energy in thermodynamic systems. It's a little different from heat or work because internal energy is the total energy stored in a system. This includes both the kinetic energy from the random motion of molecules and potential energy from the forces between particles. For an ideal gas, internal energy depends only on temperature. For example, if you heat up a gas, its molecules move faster. That's an increase in internal energy. The equation for the internal energy of an ideal gas is U is equal to 3 halves n T, where n is the number of moles, R is the gas constant, and T is the temperature in Kelvin. So when you heat up a gas, you're not just adding heat, you're increasing its internal energy, making the molecules move faster. It's like shaking a bottle of soda and making the molecules inside move faster. Alright, time to put it all together with the first law of thermodynamics, or, as I like to call it, the law of energy conservation. The first law states that energy can't be created or destroyed, it can only be transferred or transformed. The law is expressed as delta U is equal to Q, W. Here's how it works. The change in internal energy, delta U, of a system is equal to the heat added, Q, minus the work done, W. This means if a system does work on its surroundings, that energy comes from the heat added to the system. The first law essentially tells us how energy moves around in different forms: heat, work, and internal energy. Time to bring it all to life with a solve example. Let's say we have a gas in a piston. The gas starts with an initial volume of 2 cubic meters and is heated at constant pressure, expanding to 3 cubic meters. The pressure is 2 times 10 to the power of 5 pascals. We want to find the work done and the change in internal energy. First, let's calculate the work done by the gas. Using the equation, W equals P times delta V. We substitute the pressure and the change in volume, which is delta V equals 3 cubic meters minus 2 cubic meters. W equals to times 10 to the power of 5 times 1, which equals to times 10 to the power of 5 joules. Now, for the change in internal energy, we need to know the temperature change of the gas. Using the ideal gas law, we can calculate the internal energy change. The work done by the system is 2 times 10 to the power of 5 joules, and the internal energy will depend on the specifics of the gas and the temperature change. So, in this case, the work done is 2 times 10 to the power of 5 joules, and the internal energy changes based on the temperature increase. Let's wrap it up. Today, we've learned that heat is energy transferred due to temperature differences, while work is energy transferred through movement. Internal energy is the total energy stored in a system, and it depends on temperature and molecular motion. And most importantly, the first law of thermodynamics tells us that energy can't be created or destroyed, it can only change forms. So whether you're heating up a pizza or driving a car, these principles are always at play. Thanks to the first law, we can understand and control how energy flows in systems all around us. I hope you now have a clearer idea of heat, work, and internal energy. See you in the next session with more exciting physics.